Okay, so just understand this, Shomik. It's a very simple concept here. Specific heat capacity, okay? Now, suppose you have 1 kg water, right? And you want to increase the temperature of that water. Suppose this water is at a 25 degrees Celsius, okay? And you just want to increase the temperature by 1 degree. So what is the new temperature now? You want to bring it to?
26.
You want to bring it to 26 degrees. So only a certain amount of heat will be required for this. For 1 kg water to increase the temperature from 25 to 26 degrees. So your mass of water is also fixed. The amount that you want to increase, the temperature that you want to increase by, that is also fixed. So you have a fixed heat that you need to provide to it. Clear? That heat is called as the specific heat capacity. All right. That heat is called the specific heat of that particular product, component. Yes, object. Now, similarly, you have aluminum here. This is also 1 kg. And you want to increase, it's now at 30 degrees Celsius. You want to increase the temperature by 1 degrees. So it will become 31 degrees Celsius, right? This amount that is going to increase. Now, will it be the same as water or it will be different than water?
What amount? The heat required?
The heat which is required to increase the temperature of that 1 kg aluminum only by 1 degrees. Will it be the same as water or it will be different from water?
Different, lesser.
It will be different from water, and lesser, more, we'll see later that how much it is, but it will be different from water. So every element, every component that you are changing the, increasing the amount of heat, that is going to change depending on what object it is and how much you want to increase, right? What if I want to increase the temperature by 2 degrees Celsius? Then what will happen?
Twice into that.
It will be twice. What if I want to increase the temperature by 1 degree only, but my mass of water is 2 kg? Then what will happen?
Twice of specific heat capacity.
Then also twice. What if it is 2 degrees and I also want to increase the mass of 2 kg, mass to 2 kg now?
2 into 2, so 4 times.
So 4. So basically, the specific heat is the amount of energy required to increase the temperature of a
degree for 1 kg.
For 1 kg, absolutely. So what will be the specific heat capacity? How much is the energy required for completely increasing, depending on how much mass we have and how much is the degrees that we have? So that will be dependent on how much what the question is asking us. Okay, so let's come to this term, which is with this formula, which is energy is equal to mass into specific heat into temperature, which is energy is equal to, we call it MC delta T. Is my point clear?
Yeah.
MC delta T. What is M? M is the mass. What is C? That's the specific heat capacity. What is delta T? Delta T is the change in temperature that you want. 1 degree, 2 degree, 10 degree, 40 degree, whatever. That is what delta T is going to tell us. Now you tell me, in this, delta T is the unit of delta T would be how much?
Delta T will be Celsius.
Degree Celsius. Okay. What about mass? Unit of mass will be?
Kg.
It will be kg. So what is the mass of mass of energy transferred?
Kg per degree Celsius.
Energy transferred. Energy is always in joules.
Yeah.
So suppose I want to figure out the unit for this C. The unit would become
joules per kg centigrade.
Joules. You bring the kg down. You bring the degree Celsius down. So joules per
kilogram Celsius.
Degree Celsius. That's the unit for specific heat capacity. Clear?
Yeah.
Okay, next we move to a question. 2 kg of water cools from 70 to 20 degrees. How much thermal energy does it lose? It is not cooling down. So when it is heating up, it is gaining energy. When it is cooling down, it is losing that energy, right?
Yeah.
Right. So you have to tell how much of this energy is being lost.
So for energy, the formula is, I guess, mass into specific heat capacity into delta T.
Delta T. So how much is M?
So mass is 2 kg, so 2.
M is
And
2 kg. First, you write down everything which is given to us. M is equal to 2. Then
2. And specific heat capacity is 4200 joules.
4200 joules per kg degree Celsius. And delta T,
50 degrees Celsius.
it is 50 degrees Celsius. Okay, now formula.
Mass into specific heat capacity into delta T.
MC delta T. Okay, then M is
2,
C is
4200,
delta T is
50.
perfect. And you multiply this, you will get an answer in joules, right? Your answer will be in joules. Now, if you multiply this, what is the answer? Can you check and tell me, calculate and tell me the answer that you're getting? 2 multiplied by 4200.
2 more zeros.
Kitne zeros?
4 zeros.
420 and then
3 zeros.
000 joules, right?
Yeah, or for 420 kilojoules.
Or we write it as 420 kilojoules. That should be your answer. You should convert it to 420 kilojoules, which that's a because it's otherwise it's a very big number. So it's better to convert it as into a kilojoules now. Okay. So I hope this part is understood. What is thermal capacity?
Yeah.
Okay. Now one more formula that we have. Okay. That formula is, you need, please write it down. Power is equal to energy upon time.
Yeah, we had this in the exam.
Right, it's the same formula. Okay, so which means power multiplied by time is equal to energy.
Yeah.
Now, what we are calculating here is also energy. So we can get a question where we need to figure out how much is the power if the something is on for a certain amount of time. So can we figure out the power? Can you calculate the power based on this formula?
Yeah.
Okay. What is the unit of power?
Watts.
What is the unit of energy?
Joules.
What is the unit of time?
Seconds.
Seconds. So these things you should be knowing before you start doing this. Okay. Can you do question number 2? How much thermal energy is needed to raise the temperature of 1 kg of copper by 1 degree Celsius? So what do? There is a table given to us. You go and check how much is copper. What is it? What is the value of copper?
400.
400 joules per kg degree Celsius. So how much is the specific heat?
400.
Thermal energy. That is 400. So for the first one, the answer would be 400. Now, rest of the calculations, you will tell me how to do.
Okay, so energy change is, I guess, minus 50 degrees.
So
It's still giving out, so it should be 50 degrees only.
Okay.
Mass is 10. C is 400 and delta T is 50. So 10 into 50 into 400.
M, C, and delta T. Answer would be how much?
20000.
Kitna hua? Can I say 200 kilojoules?
Yeah.
Now, if in part B the copper were replaced by water, how much thermal energy would it give out?
In part B. Oh, okay.
In
So
part, what if I change it to water?
yeah,
Same
so 50
question.
into 50 into 4200.
Into this. Okay, which is how much?
2150.
2100 kilojoules.
Yeah.
Now, can you see one very important thing? One very important thing here. You have a stomach pain, you have a headache, you always use water bag. Why?
Because of its high specific heat capacity.
Exactly. And it is able to give out a lot of heat for a very long time. It has, because the specific heat capacity is so high, it has a lot of, it can hold a lot of heat into it. Which other things will cool down very quickly or become hot very quickly, both. But water will take time to get heated up, but it will take time to lose that heat also. So you understand what is the reason behind the specific heat capacity, right?
Yeah.
You can yourself see almost 10 times heat is being given out by water.
Oh,
Almost.
what determines specific heat capacity? Like why is it different for everything?
Okay. So basically it is
Density?
this, huh?
Is it density?
It is density. It's also the structure, not just density, it's also the structure in which it is being made. Something is getting cool, and something is getting hot. Both also depends on the structure, because the structure has to break. It's the thermal, uh, you know, so it takes time to break the bond. It takes time to bring the bonds back. It's the same thing here. Did you get it?
Yeah.
Next is third question.
Energy. So again, 2 into 1 into 4200. So 8400 joules.
Tell me let's go step by step. How much energy is needed to raise the temperature of 2 kg of water by 1 degree Celsius? So 2 kg water. So
kg
2 and
into delta T, which is 1,
1,
into C, which is 4200.
which is equal to how much in all?
8400
8400
joules.
joules. Okay. How much energy does the heater supply?
210 joules.
And how do you know that?
Its power is 210 watts, so it supplies 210 joules per second.
So 210 uh, uh, is equal to, that's wattage, is equal to energy upon time, and time is 200 seconds, right? So what did you say? How much energy upon time would become 210 watts multiplied by 200 seconds? What's your answer for this? What did you give me your answer as?
But no, 210 watts heater. Now, so the heater is, what is the question? Oh, okay, fine. Overall, yeah, sorry. So 210 watts into 200 seconds.
So which is equal to how much?
42000.
42000, right? That's the energy, right? That's the
Yeah.
energy, correct? So this much of energy is the heater able to provide, right? Right? That's the heater which is able to provide when it is on for 200 seconds. Assuming that no thermal energy is lost. What is the temperature rise of the water? Did you get the question?
Yeah.
So can you tell me now, what do we need to find out in this question now?
We delta T.
We need to find delta T, and what all things are given to us?
Mass is there, I guess. Yeah.
Mass is there. Mass is how much?
2 kgs.
2 kgs.
Specific heat capacity is 4200.
4200.
And delta T we need to find. We have thermal capacity or energy.
So we have E, है ना? So
E.
यानी कि 42,000 should be equal to 2 multiplied by 4200 multiplied by delta T.
Yeah, so
Right?
we take both of those on that side. And so 42,000 upon 2 into 4200.
So that is 2 into 42 would be 8400 is equal to delta T.
That's 5.
That is a temperature of, so let me just check.
5 degrees.
1000 divided by 8400, which is equal to 5 degrees Celsius. That's your
Answer.
So got this one?
Yeah.
Any confusion in this?
No.
Now we come to something very important, that is your latent heat of fusion, latent heat now. And latent heat of, we have latent heat of fusion and we have latent heat of vaporization. Okay? What is it? First, let's understand.
Amount of heat needed to change state. So
change
like
the state.
to melt or to like vaporize.
Right. So what happens here? You had ice, you're heating the ice. Okay. So when you're heating the ice, obviously the temperature of the ice is increasing. Okay. So suppose it was at minus 20 degrees Celsius. Now you're increasing the heat. Ice is slowly moving toward from solid to it is slowly breaking the bonds inside. I mean, it is slowly the temperature is changing. So what you see is the coolness of ice is reducing, but it is still ice. Okay. But once it has come to a temperature of 0 degrees, no matter how much you're heating it, it's still not increasing the temperature. I'll repeat. Ice is at 20 degrees, minus 20 degrees Celsius. You heat it, the temperature is increasing. You're putting a thermometer and checking again and again. Lekin, the moment it reaches 0 degrees, for some time, you see that there is no increase in temperature, which is happening earlier.
Yeah.
Why is it so?
Phase change.
Huh?
The, I guess, ice goes into phase change and does not increase in temperature till it has fully changed into liquid.
Absolutely. So in that time, even though you're heating it up, you're providing energy. All of that energy is going into the ice to break all the bonds, right? So you're breaking the bond. When the bond breaks, then what happens? All of this is now, all of this energy that you're providing is just used up to break those bonds. Now what happens? After a certain point of time, all of that energy is now done, and then it goes into changes into the state of liquid. Clear?
Yeah.
Clear? So solid, so wherever there is a phase change, you will see that is called, now this is that there is heat inside, but that heat is not visible. That's why it's called latent or hidden heat. Got it? Now this latent heat can be of two types. It is latent heat of fusion or latent heat of vaporization. Fusion, when what happens?
Melting.
Melting.
Or solid to liquid change.
Solid to liquid will be fusion. Now same thing will happen when liquid is heated up, temperature will increase. Yeah. Liquid reaches the boiling point, the temperature will stop there. It is not going to increase because now all of that heat is used to break the bonds. Right? Once the bonds are broken, that means liquid is changing into vapors. Once the bond is broken, liquid is completely converted into vapor. Clear? Once that is done, then at that time, for some time, that latent heat is still there. That latent heat is called as latent heat of vaporization. Clear? So latent heat of fusion is at the melting point. Latent heat of vaporization is at the boiling point.
Yeah.
Clear? Okay. Okay. Now, like the way we had a formula for specific heat capacity, we also have a formula for latent heat. And what is that? Mass is equal to specific latent mass into specific latent heat is equal to energy transferred. All right. So E is equal to M into L, where L is the specific latent heat. Okay. So for example, we have 2 kgs of ice. Okay. And that ice, so and the latent heat is for ice is 330 000. How many zeros? 1, 2, 3, 4 zeros. I made one extra zero. I'll just remove that. That is your
Latent heat of fusion.
correct. Latent heat of fusion.
For 1 kg, no? Or is it for 2?
Per kg. Per kg. That's for 1 kg. Now you're supposed to tell me how much energy will be transferred from here. So that will be 2 multiplied by this. For 1 kg, it is this much. So for 2 kg, it will be 2 multiplied by this with the latent heat.
000.
Right. So yeah, you know that, right? And in kilojoules, it will be 660 kilojoules. Clear? Okay. Again, here also we have the same thing, power related question. Power is equal to energy upon time. So you can have a question based on that. Let's, you understood what will happen for vapors, right? So there will be a latent heat of vaporization. Do you think latent heat of vaporization and latent heat of fusion will be the same value?
No.
No.
Gas,
Right?
liquid molecules are more far apart, and gases is even
Right.
hard, so it takes more energy.
Absolutely. Okay. So
2300, I guess, kilojoules of energy.
right. So Abham, we will do a question based on this. Okay. Read the question number 1. Read it aloud.
Some crystals were melted to form a hot liquid, which was then left to cool. As it cooled, the readings in the table below were taken. What was happening to the liquid between 10 and 20 minutes after it started to cool?
No.
So,
Can you answer this? You're on mute.
yeah, I'm just looking at the table. Okay, so 10 to 20 minutes, the temperature stayed constant because it was, I guess, changing state or phase.
Okay. So it's changing phase. Can you predict the phase?
Yeah, so solid to liquid.
Is it melting or
Liquid to solid.
liquid to solid?
Yeah.
Acha. So it is not, it's the other way around, which means you're cooling the thing up. You're reducing the temperature, cooling the thing up. Okay. Next. Next.
Melting point of the crystals, I guess, is 68.
Melting point is 68. Okay.
That's it.
Next, second part. Second question. Energy is needed to turn water into water vapor. How does the kinetic theory explain this?
Yeah, okay. So, well, kinetic theory says that more So liquids, I guess the particles move around a little in liquids and they move around a lot more in gases. So, and this moving around is basically stored up kinetic energy in the particles. So as you heat it up and supply it with more energy, the particles move around faster and then I guess at one point change state into gas.
Okay. Question number 3.
Okay, so that is 3, 3. So latent heat of fusion, ice into water. Yeah, so fusion is 330 kilojoules. So that's for 1 kg. So for 10 kg, we multiply that by 10. So that 3300 kilojoules.
What about the other one?
So not specific. Latent heat of vaporization of water is 2300 kilojoules per kg.
Mhm.
So for 10 kg, you multiply it by 10. So that is 23,000 kilojoules of
Very
energy.
good. So you're able to identify when to use the latent heat of fusion and when to use the latent heat of vaporization. That you're clearly, that's what one of the most important applications here is. Okay. The next kind of question that you will see in the past papers is when you're supposed to figure out that you figure out the energy and you connect that energy with your chapter of electricity where you find out the electrical energy. So you get a lot of questions in the past papers based on this.
How do you do that? The electrical energy thing?
Once you will do the electricity chapter also fully, then you will see the connect. So I will be doing those questions also when we are done with both the chapters. I'll show you how to do it. Okay. For now, these are based on just one formula here. Can we do the question number 4 now?
460-watt water heater is used to boil water, assuming no thermal energy loses. What mass of steam will it produce in 10 minutes? Okay.
The time has to be in minutes or
Hmm?
time should be in minutes or seconds or hours. क्या होना चाहिए?
What we had was what? Seconds.
It should always be in seconds. So you need to convert.
Should be 600 seconds.
600 seconds. Okay. So it's 460 multiplied by
So 460 into 600.
that is your energy.
Yeah.
Okay.
What mass of steam? So we need 2,300 kilojoules for 1 kg. What do we have? 1 second. We have 276 kilojoules of energy. So I guess you divide that by 2,300.
2,300,000. It's 2300 and then you because your answer is in joules only, no?
Yeah. Okay. So 460 into 600. 276,000 divided by 230,000. 5 zeros.
So your answer is how much?
0.12 kgs.
0.12 kgs will be
120 grams.
120 grams only.
Yeah.
Question number 5. A.
Where, yeah. The table gives the melting and boiling points for lead and oxygen. Lead's melting point is 327, boiling point is 1744, oxygen is minus 219 and 183. At 450 degrees Celsius, will the lead be a solid, liquid, or a gas? Liquid. Lead will be liquid at 450 degrees Celsius.
Mm-hmm. Reason?
Once it reaches 327 degrees, it will melt.
Very
And to
good.
boil, it needs to reach 1744, so not even close. So it will be in the middle, 450. So
Very
which is
good.
liquid. Minus 200. Again, once it reaches minus 219, it will melt and turn into a liquid. And staying at minus 200 will mean it does not have enough energy to be able to boil, which is it reaches that at minus 183. So minus 200 will be again liquid.
Hmm. Okay. Then further, graph shows how the temperature of a pure substance changes as it is heated. At what temperature does the substance boil?
Around 440 degrees
Hmm.
Celsius.
Okay, sketch the graph and mark within X any point where the substance exists as both a liquid and a gas at the same time.
Anywhere on the flat line at 440.
Okay, then all substances consist of particles. What happens to the average kinetic energy of these particles as the substance changes from liquid to gas?
It increases
What increases?
kinetic energy.
The average kinetic energy is increasing. Okay, then explain in terms of particles when and why energy must be given to a liquid if it is to change to a gas.
So that it has enough energy to be able to move, for the particles to move apart and turn into a gas.
Hmm. Okay. Okay, this C part. Question number 7. Question number 7, C.
Which is question 7, left one.
Here, here. Should I mark
Yeah, because I can only see 9.
this one?
Okay, okay. It has a power output of 3 kilowatts. What is the K stand kilo?
Hmm.
How much energy in joule does the heater deliver in 1 second? 3000
3000 watt
joules.
joules. Hmm.
How much energy in joules does the heater deliver in 7 minutes? So 7 minutes is 420 seconds, right? So 420 into 3000. 60,000. 1 second. 12,60,000 joules, which is also
60,000 joules. Okay.
1,260 kilojoules. But they're asking in joules.
Hmm. In joules only they've asked. Yes. Next.
The tank holds 100 kilograms of water. The specific heat capacity of water is 40 to 100 joules per kilogram degree centigrade. Celsius. I keep saying centigrade. How much energy in joules is needed to raise the temperature of 1 kg of water by 1 degree? 40 to 100 joules.
Hmm.
How much energy in joules is needed to can't read the rest.
1 second. How much energy in joules is needed to? Okay.
The seventh end is on top.
Hmm. On top.
Oh, yeah. Raise the average temperature for all the water in the tank by 1 degree Celsius.
I think you need to see the previous part also, right? For this.
Probably.
How much energy in joules is needed
100
to?
kgs of water. Okay. So, yeah. So 100 into 4200. So that is 420000 joules.
Okay. Third part.
If the heater switched on for 7 minutes, what is the average rise in temperature of the water in the tank? So the heater was giving us, can you scroll back? The
Mhm.
heater was giving us, what heater? Where is it? 3000 kilowatts. So that is 3000 joules per second.
Okay.
So if it
Mhm.
was switched on for 7 minutes, once that I had gotten the answer. 12,6 3,000. So 12,60,000 divided by 100 divided by 4,200, which is 3 degrees Celsius.
Okay.
Wait, what is the question? 3 only, no?
Yeah. Now I wanted to do the ninth question.
Boiling point of the graph below shows how the temperature of some liquid in the beaker changed as it was heated until it was boiling. What is the boiling point? 80 degrees Celsius.
Uh,
What difference, if any, there would be in the final temperature if the liquid is heated more strongly? There would be no difference in temperature, but there would be a difference in the amount of time it would take to heat.
Very good.
And it would be quicker. State one difference between boiling and evaporation. Okay. So I can give like two, three. Boiling takes place throughout the entire beaker or the container, while evaporation happens on only on the top of the surface of the water. And boiling happens only at the boiling point. Evaporation will take place at any this thing temperature.
Mhm.
Boiling is faster than evaporation. That's it.
That's it for us.